Hello and welcome to Diplomatic Derivatives, a platform where we talk about multiple concepts in pure mathematics and international relations. We have started the series of the group theory, that's part of the pure mathematics portion, and we have done multiple topics including groups, subgroups, cyclic groups, and certain theorems related to cyclic groups. Today we are going to jump to another concept, which is the cosets. Now, with the help of this concept, we will be able to do an important concept of the group theory, which is the Lagrange's theorem. For that purpose, we need to understand what are cosets. So let's see. Let G be a group, H be a subgroup of G. Now we have already done the meaning and understanding the entire concept of subgroup. So for that, make sure you check the previous videos and also the link in the I button to see the video about subgroups. Now H is a subgroup of G and G is an element of capital G. This means that this small letter g is part of the main group, that is capital G. Now, then the left coset of H with respect to G is. Now, the cosets are of two types. You can either have left cosets or you can have right cosets. Now, the basic concept is that when we have a subgroup, what you do is that you take one element from the main group, okay, so let's suppose that's small letter g, and you multiply that element with each element of the subgroup or whatever the operation is. If its operation is addition, so you add with each element of the subgroup. So you take any element from the main group, perform the operation of that element with all the elements of the subgroup. That is known as a coset. So the set you're left with is the coset. Okay, now this can be done in two ways. Either you perform the operation from the left or you perform the operation from the right. So in the case of the left coset, you take the element from G, you multiply that element with the subgroup H. So you get a set which is G, this is from the group, and this H is from the subgroup. So let's suppose if subgroup H is H1, H2, H3 and H4. So all the elements of the coset will be G, H1, G, H2, G, H3, G, H4. Okay, that's how you perform the operation and you get the coset. Okay, then you will be doing this operation a number of times depending on the number of elements in G. So if you have, let's suppose, 4 elements in G, so if you are having 4 elements in G, and what you do is that you take these 4 elements, one element at a time, and perform the operation, and what you get is one coset. Then you take another element, you perform the operation, you get another coset. So in this way, you are going to do it 4 times, therefore you're going to get 4 left cosets, and similarly you will be getting 4 right cosets. That is, you are going to perform the operation from the right. So so the number of cosets depends on the number of elements in the group. Okay. Now, before taking an example, we just have to understand a few points. All cosets of a subgroup have the same number of elements as the subgroups. Now we're talking about the number of elements inside the coset. For example, if the subgroup has number of elements as 2, there are 2 elements in the subgroup. Let's suppose those 2 elements are 1 and 2. Okay, so this is a subgroup H. It has 2 elements. Therefore, when you perform the operation, you will get one, let's suppose you're doing it from the left. So the coset that you get, that the left coset also will have 2 elements. How? Because if you take an element from G, let's suppose you are taking 1. So you multiply 1 with this element and 1 with this element, right? At the end, you're getting 2 elements inside the set, right? So that's going to be one of the left coset. If you're doing it from the right, you multiply from the right and then you get a right coset. So the point is that the number of elements of the coset are equal to the number of elements of the subgroup. Not the elements. The elements are not the same. It's the number of elements that are same. Cosets are either disjoint or exactly the same. They do not overlap partially. So either 2 cosets could be exactly the same or they could be disjoint. So there is no overlap. There is no common element between any 2 cosets. For example, we have 0, 8 and 1, 4. These are 2 cosets. There is no common element and they are disjoint. There is nothing similar in these 2 cosets, and it's always going to be the case. Third point is the cosets partition the group G, meaning every element of G is in exactly one coset. So all the cosets of a group will be having all the elements of the group in exactly one of the cosets. So you won't have any coset which is not going to have an element from G. So if the point is that all the elements of G must be inside the coset, there should not be any element of G left out. All elements must be inside the cosets. For example, if we have G is equal to 1, 2, 3, 4 and we have a subgroup H which is 1, 2. So what you do is you take one element from G. Let's suppose you're taking 1. And the operation is multiplication, let's suppose. So 1 multiplied with 1 you get 1, 1 multiplied with 2 you get 2. This is for the first coset. Then 2 multiplied by 1 you get 2, 2 multiplied by 2 you get 4, the second coset. 3 multiplied by 1 you get 3, 3 multiplied by 2 you get 6. Then again similarly 4 multiplied by 1, 4 multiplied by 2 and you get 4, 8. Now all the elements of the group are in exactly at least in like we have all the elements of the group inside the cosets. There is no single element left out. Okay, so this is what this point means, that all elements of the group must be inside the cosets. There should not be any single element left. Then we have the number of distinct left or right cosets is called the index of H in G, written as GH. Now this we will be able to understand with the help of an example which is going to be in the next slide. So just to make it clear, what is an index? The number of distinct left cosets or the right coset. This is known as the index. We'll understand it with the help of an example. Let G is equal to Z6. So this is a modular group. We have also done this before. Z6, which is equal to 6 is the number of elements starting from 0 since it's integer. So we have 0, 1, 2, 3, 4, 5 under addition modulo 6. So the operation is addition. Okay, now we are going to, whatever cosets we are going to make, they are going to be made with the addition operation, not multiplication. Okay. Let the subgroup H is equal to 0, 3. Now this is one of the subgroup of this main group. Okay. Left cosets. Now how do you make the left coset? First you take one element from Z, which is 0, and you perform the operation addition from the left. Okay, so you perform 0 on H from the left. So you get 0 plus 0, you get 0, and 0 plus 3, you get 3. This is the first coset. Next you have 1. 1 plus 0, you get 1, and 1 plus 3, you get 4. So you have 1 and 4. Then you have 2 plus H, because the third element is 2. So 2 plus 0, you're adding from the left. 2 and 2 plus 3, you get 5. Then similarly 3 plus H. 3 plus 0, you get 3. 3 plus 3, you get 6. 3 plus 3 is 6, right? And since this is a modular group, 6 will be equal to what? 0. 6 is assigned to 0. So you get 3, 0. This 3, 0, now the point here is equal to this 0, 3, because in any order you write the number, it's the same, right? Either you get a set which is 0, 3 or 3, 0. It's both the same, right? Therefore, when you perform 0 plus H or you perform 3 plus H, you get the same answer. Okay, so this is equal to the first one. Again, you perform 4 plus H, so you are getting 4, 1, which is same as 1, 4. So you get same as the second one. 5 plus H, 5, 2, which is same as 2, 5, which is same as a third one, right? So now you have done all the left cosets. You have all the elements of the main group added from the left to the subgroup, and now you have the cosets. All right. Now we come to the point as we talked in the previous slide about the index. Now what is the index? Index is a number of distinct left or right cosets. Now distinct here means not the same ones, so different ones. That is, you have 0, 3, you have 1 plus H, you have 2 plus H. So you have 0 plus H, you have 1 plus H, and you have 2 plus H. The rest of the 3 are repeated, right? The distinct ones are only the first 3. So these are the distinct cosets. And in a similar way, you perform for the right cosets as well. So you add from the right. There are 3 cosets, each of size 2. Total elements is equal to 6, which is equal to the order of the group. This is about the part where we said that each element of the group will be inside each of the coset. So all elements will be present inside the coset. So what we're saying is when we get the index, we have 3 cosets which are the index. Each coset has a size 2, right? The total elements therefore are 6, which is equal to the order of G. If this is true, what we did is we multiplied the index with the size of the cosets. Okay, therefore that will become the total number of elements of the group. If this condition comes true at the end, it means that our cosets are correct. Okay, and in a similar manner you perform for the right cosets. So that this is a very basic concept, and it's very important as well as very simple. Now, what are the importance of the cosets? They are used to prove the Lagrange's theorem. This is the most important thing, Lagrange's theorem, which will be understood, which will be tackled in the next video. Define normal subgroups, again, another concept coming in the future videos. Construct quotient groups, that is factor groups. So this also will be looking at in the future videos. So therefore, first we need to completely make sure that cosets are clear before moving on to the next topics. Okay, thank you. That's all for this video. I hope you understood the concept of cosets. We'll be looking at further concepts in the future. Make sure you like, share and subscribe my channel. If you have any questions, make sure you ask them in the comment box below. And that's all for today. See you in the next one with the Lagrange's theorem. Thank you.